Everybody got our information sheet? You may well have downloaded it before yesterday. It's available on our Sockeye website. It's also available on the internet website. We decided that rather than using acid-base table which you see in the notes, you might as well use the acid-base table on the information sheet, since in addition to the acid-base table, the information sheet contains a bunch of other useful information, much of which will be regularly used on quizzes and exams. You get this sheet for each quiz and each exam. I don't expect you to memorize this stuff. We expect you to be able to use it. And today we will begin discussing how you will use the information in the Bronsted-Lowry acid-base table in order to be able to figure out what in fact are the principal ingredients of a chemical system, like a water solution. This, I'm sorry to say, is what textbooks do not do at all. I don't understand it. Because if we are to be able to understand the chemistry that occurs in the system, and a very common system, a system that is very often studied in first-year chemistry, like what you're going to do in general chemistry laboratory 2046. And you already did this in 45, 46. Is to conduct and study reactions which take place in water solution. And most water solutions are colorless systems. What's in this system? Because if you want to know what chemistry takes place in the system, you can't possibly understand it or know it if you don't know what the heck is in the system. So to get at system contents, principal system contents, I've created the term principal system inventory. I had originally called this principal species inventory, which you see in the notes. But principal system inventory is better. So we'll use that instead. Because it must be the case that if in a system like a solution or reaction of consequence occurs, it's got to involve the principal system components. And if you don't know what those system components are, you can't possibly understand this reaction. You can't possibly write an equation for the reaction. Which is why every reaction written for a reaction that occurs in water solution in textbooks is wrong. Because they don't pay attention to this very important consideration. We're not going to make that mistake. So before we elaborate on principal system inventory, which you all started to talk about yesterday, so when we get to the system inventory stuff, a lot of what I will say is stuff you already heard yesterday. I repeat this by intention. This is important. And it's an aspect of chemistry which you've never dealt with before, except in 45 laboratory last term. Remember doing this? Well, now you're going to see why this is so doggone important. But before we tackle this, we look at another aspect of principal system inventory for water solutions, for solutions in which chemistry is to be studied. Like water solution. Like ammonia solution. Interestingly enough, a number of Bronsted-Lowry acid-base studies have been made in liquid ammonia. You have to be bundled up when you do this chemistry because in order for ammonia to be a liquid, you've got to be operating at about minus 30 centigrade. That's kind of cold. You know what this top liquid is here? This simplest known alcohol. It's oftentimes called commonly wood alcohol, because lumber contains this stuff. Methanol. I don't care about the name, the formula that counts. The name for this is in the notes. You see it? I don't even remember the name myself. It doesn't matter. Methyl hydroxyl would count more than anything else in the formula. Because when it comes to principal system inventory, the leveling effect tells you in water solution, the strongest acid that you can have present at high concentration is hydronium ion. And how does hydronium ion relate to water? You learned at the very start of conversation in chapter 18 that when you take the formula for a species and add H plus to it, you have now written the formula for the conjugate acid of that species. And hydronium ion is the conjugate acid of water. Because any acid that's stronger than hydronium ion, like HCl for example, on being dissolved in water by reaction with water, converts, practically speaking, to an extent of 100%. The hydronium ion and the conjugate base of HCl is chloride. Which is why we've already reminded you. When you see the formula written HClAQ, unless the hydrochloric acid solution in question is more concentrated than about 8 molar, there's no HCl molecules in the solution. Yeah, you prepared it by dissolving hydrogen chloride in water. That's how you make hydrochloric acid solution. But if you refer to the contents of that solution after you prepared it, with this formula HClAQ, you're lying. There are no HCl molecules in there. So why textbooks insist on doing this, I do not know. Doesn't make any sense. Hydronium ion, chloride ion, and water are the principal components of hydrochloric acid solution. That's the PSI, not HClAQ. Well, it's easy to prove. Just do conductivity studies, pH studies, all kinds of ways to prove it. Now then, if I dissolve a base in water, and it's a stronger base than the conjugate base of water, the conjugate base of water, hydroxide ion, HO minus. If this base is stronger than hydroxide ion, it will react this original base with water to an extent which is on the order of 100%. In many cases, it is 100%. And convert the hydroxide ion and the conjugate acid of the base which was dissolved. So if you look at the acid-base table, do that right now. You use the one that's in the notes or the one that's on this information sheet. Please, if you will, from now on, always have the information sheet with you. Every class gathering. Everyone uses information regularly. On the information sheet, you see that in the base column, given that the bases are ordered in, or arranged in order of increasing strength from top to bottom, the strongest bases are at the bottom of the base column. And the only two bases on our table which are stronger than hydroxide ion, sulfide ion and oxide ion. So, if I go to the laboratory and I see this bottle, in other words, I see a reagent bottle which has this label on it. 1 capital M Na2S. What does that mean? It means that when this solution was prepared, per liter volume of solution, 1 mole of the ionic compound sodium sulfide was dissolved. That's what this means. And when ionic compounds dissolve in water, what do they always do? They dissociate. But that may not be the end of the chemistry. We know at the minimum, the ionic compound will dissociate. So at the minimum, when I make this solution, I'm creating a solution which in it has got sodium ions and sulfide ions, initially. Will I ever have, will it be the case that I will ever find sulfide ions in the solution after I make the solution? Can I find sulfide ions in this solution after I make this solution? Yes or no? The answer is no way. Because these sulfide ions are stronger bases than hydroxide ions. Table tells you that, doesn't it? That means when I put sulfide ions in solution, this reaction occurs. To what extent does it occur? How much? 100%. This is all information. And by now you should be familiar with it. By definition, strong acid is hydronium ion, the water solution, and any acid stronger than hydronium ion. So when you look at our acid-base table, you see we've got 5 strong acids listed. Hydronium ion, immediately above nitric acid molecule, and the hydrochloric acid molecule, and the sulfuric acid molecule, and then the perchloric acid molecule. Strong bases in our table: hydroxide ion, sulfide ion, and oxide ion. So what this leveling effect is reminding you about is that if I am doing acid-base chemistry in water, that's my solvent, the strongest acid I can ever have at high concentration is hydronium ion, the conjugate acid of the solvent, and the strongest base I can ever have at high concentration is hydroxide ion, the conjugate base of the solvent water, as illustrated by this reaction. If this thing's going 100%, when I put a source of sulfide ion in solution, like dissolving sodium sulfide, do I have, after this solution is prepared, do I have any of these in the solution? No, they all reacted. So if you write sulfide ion AQ, which these damn dumb textbooks do all over the place, you're writing a lie. There's none in there. Chemistry can't occur with this. There's none left after you make a solution. All of these put in solution reacted with water and became hydrogen sulfide ion and hydroxide ion. So there's our PSI. Hydrogen sulfide ion, hydroxide ion, and of course water the solvent itself. All right, so back to this leveling effect. Again, I remind you that a number of acid-base studies have been done in solvents other than water. Quite a number. But by far the most common acid-base chemistry system is water solution. I provide you with an example. Me, just like you. Because damn near every reaction of consequence that occurs in our body takes place in water solution. You believe that? That's why I argue. In first-year chemistry, we need to make a big deal about chemistry that occurs in water solution, because this world in which we live is a water-solvent life system. And based on what we now know, that ain't never going to change. So that's the chemistry we ought to emphasize. In fact, throughout chemistry, that's the chemistry we ought to emphasize. Do you think it's important to understand the chemistry of life? I don't think I need to give you any sermons on that. Chemistry of life and life support systems, like oceans, and rivers, and streams, and rain, and blood, and sweat, and tears. Back in my day, a well-known rock group. But certainly examples of very important life systems, with water being the solvent. We're going to make a big deal about chemistry that occurs in water solution because it's the chemistry we need to know about, and it's certainly the chemistry which you know most about regarding any chemistry you may know at this stage of the game. But if chemistry is studying ammonia, that's the solvent. Then my strongest acid that can ever be present at high concentration is the ammonium ion. And there's formula H4N+. Not NH4+ like the damn textbooks write it. Because formal charge analysis on this, the ammonium ion, shows you the charge of positive charges on nitrogen. So that's what we ought to write. Strongest base, whichever can be present at high concentration in the solvent, is this, the amide ion. I don't care about its name. But again, the charge is on nitrogen. Formal charge analysis of this formula shows you that. So H2N minus. Now to be sure you know how to play the game, right now on your paper, I want you to write the formulas for the strongest acid which can be found at high concentration in either of these liquids used as a solvent for acid-base chemistry studies, and also the conjugate base. Do that right now. Now, while you are pondering this issue, you think it might be necessary and appropriate to ask the question I just put to you, to write the Lewis pictures for those things? Think it might be necessary to get into structures? Get at it. Did you get these Lewis pictures? Question. And you did stuff like this in 2045. And now we need you to not only know it, but to put it to use. HCOH. The way I wrote on board. Is this a linear arrangement of atoms? Yes or no? How's the carbon in that molecule hybridized? How's it hybridized? sp3. Does it have four peripheral atoms connected to it? You betcha. So if I focus on the geometry shown by that carbon atom and the three hydrogen atoms and the oxygen atom which are covalently connected to it, what kind of geometry will I observe? Tetrahedral. How's the oxygen atom hybridized? How is this oxygen atom hybrid? sp3. Was this a linear arrangement of atoms? Hell no. How about here? HCNOH. You know, if I want to type this in the textbook, it's awfully tough to type this to keep with its geometry. This shows me its structure, but it doesn't show me its geometry. Is this a linear arrangement of atoms? Hell no. sp3, sp3, sp3. I'm looking at a zigzag pattern. All sp3 hybridized atoms. Now let's get back conjugate acid? Well, I think at a glance you can recognize that if H plus approaches this molecule and is to make a covalent bond connection with this molecule, the only place it can readily do so is with one of these presently non-bonding pairs on the oxygen. So I'll use this one. Doesn't make a difference. These non-bonding electron pairs are equivalent. So there's my conjugate acid. And in forming it, I will create a positive charge on the oxygen. Orbital charge analysis shows you. Now let's take the conjugate base. Now the system gets a little bit more complicated, doesn't it? Because I could take H as H plus carbon, or I could take H as H plus oxygen. Which H plus is H plus? Is it a toss-up? Is it sometimes from carbon, sometimes from hydrogen? Is it 3 times as frequent from carbon, because I got 3 times the number of hydrogen atoms here? There's not much Las Vegas stuff that goes on in chemistry. So I'm going to now draw 2 pictures. First, we imagine that H leaves as H plus from carbon. That'll leave the previously bonding electron pair as a non-bonding pair on carbon, and in so doing create a minus charge on carbon. If the H loses H plus, and the H gained from carbon. On the other hand, if the oxygen-bound hydrogen leaves as H plus, I create this ion. So the answer to the question depends on, is it the case that I will create a minus charge on carbon or oxygen? How do you vote now? Or in 2045? Did you learn that it was a lot of fun, F-O-N, to talk about electronegativity? A lot of fun. Fluorine, oxygen, nitrogen. Fun. F-O-N. Fluorine, oxygen, nitrogen. Now, chlorine and nitrogen are very similar in their properties of electronegativity. But there's a hell of a lot more important molecules with nitrogen in their composition than there are with chlorine. For whatever it's worth, I contend that an amino acid of protein is more important than sodium chloride. So I'm sticking with fun. Do you know what electronegativity is? If I asked you all to write a working definition of electronegativity, I'm curious what you would write. Maybe I'll put that on the first quiz. I do this stuff all the time. Because what I'm trying to find out is what you understand, not what you heard about. I chat about this kind of stuff often with my 2045 instructional colleagues. And they keep telling me they all heard about this. And I tell them, hearing about it ain't good enough. They got to understand it, damn it. And I find few folks like yourself, and it's not your fault. I find few folks like yourself who at this stage of the game can really tell me what electronegativity is. So I'll tell you. And I hope that this is what you have in mind now before I speak. It is an important property of the molecule, partly of an atom, important property of an atom, which depends on Z effective. You learn about Z effective? Effective nuclear charge. And provides a measure of the ability of the atom in the bound state, covalently bound state, to stabilize valence electron density. Does that sound like what you knew about electronegativity? You learned about this in 45. You learned that originally chemists had recognized they had to come up with some way to understand and explain why some atom would stabilize negative charge better than other atoms, or positive charge better than other atoms. And they tried electron affinity. Didn't work. They tried ionization in it. That didn't work. But they came up with a unique blend of this kind of stuff. I think the first guy who figured this out was Linus Pauling. Linus Pauling, wonderful guy. Won 2 Nobel Prizes. I wish it was still one. I wish the world was full of people like Linus Pauling. Because I'll tell you one thing. If the world was full of people like Linus Pauling, there would be no nuclear weapons, period, none. Because people like Linus Pauling would not have ever allowed the construction of such. And the peoples of the world would not live in the threat of nuclear war. And there's a lot of loony bastards in this world right now who, believe you me, if they get their hands on nuclear weaponry, they will not hesitate whatsoever to use it. Because they think the other world is better than this world. Well, if they want to go to the other world on their own, I don't care. But when they want to talk about taking me with them, then I care. Or people I care about, like my loved ones and my friends and like you. Then I care. And then I'm going to fight. For beliefs of that nature, even though Linus Pauling won a Nobel Prize for working chemistry, principally on the nature of the chemical bond, which led to his origination of the concept of electronegativity and other stuff like that, his most important, as I see it, Nobel Prize was for human cause.
Saying you wouldn't have allowed nuclear weaponry to happen, I mean, it's kind of, it has a duality because it's also used for food energy as well as...
Oh no, I'm not saying, we would certainly use nuclear stuff for energy.
It's opportunity that you can create it to make bombs, not to enrich the soil so that we can create agriculture. I mean, it's saying that you could, then we could just say, anyone else would stop power from making bombs.
Well, I'm saying if the world was full of people like Linus Pauling, there would be no one would have the desire to do this. You understand? I understand that we're not going to be able to do this by law, something like that. That's what this damn gun debate is all about. I have strong feelings on this gun issue, but I'll try to minimize the amount of politics that it is. Get back on those. So this is it. Because oxygen, with a much higher electronegativity than carbon, does a much better job of stabilizing negative charge density. Put another way, this species right here, this species is, you fill in the blank, with much more or much less. This species is much more or much less reactive than this. Much more or much less. This species, if I put a minus charge there, would be much more or much less reactive than this. Much more reactive. That's why you don't get that. The way molecules behave is, in whatever environment they are placed, achieve the greatest degree of stability, peacefulness, low reactivity that they can. That's just the way nature operates. All right? Now let's look at this one. Conjugate acid. Aha! Now the plot thickens even more, doesn't it? Because now an H plus approach to this molecule. It has two sites of attachment. This electron pair. Or one of these. Where does this H plus go? Well, the answer depends on which of these electron pairs is more reactive, doesn't it? Put another way, there's a nitrogen atom, a neutral nitrogen atom, like this one, with a non-bonding pair. A stronger base or a weaker base than a neutral oxygen atom with a non-bonding pair. Which is the stronger base? The nitrogen atom with the non-bonding pair or the oxygen atom with the non-bonding pair? Which is the stronger base? Sounds like we got a problem with the jury. All right, I'm going to write something else on the board. Look at the acid-base table. Because electronically, the nitrogen atom and ammonia is just like the nitrogen atom in this molecule. The oxygen atom and the water molecule is just like the oxygen atom in this molecule. Which of these is the stronger base? Ammonia or water? The acid-base table tells you that, doesn't it? And we're going to talk about stuff like this in detail when we get to chapter 23, but there's no reason not to discuss it, at least in brief right now. These seeds in your diet, which later on will fertilize, and therefore they will grow. They will sprout. They will develop. They will enrich your appreciation and understanding of chemistry. Why is ammonia a stronger base than water? I'll give you a clue. We just talked about why. Why is the ammonia molecule's non-bonding pair more reactive than either of the non-bonding pairs on the oxygen atom and the water molecule? Why?
Oxygen more electronegative.
Yes! That means this oxygen atom is stabilizing its non-bonding electron density more effectively than this nitrogen atom. Since this electron pair is not stabilized as effectively, because the EN of this or the EN of this is more reactive. So that's where H plus goes. See how powerful this electronegativity gadget is? Did you do any stuff like this with electronegativity in 2045? Because this is what the heck you should have been doing. Did you? Did you? I'm not blaming you. I want more ammunition to go after my people who are doing it the way it's supposed to be done, damn it. I want you to understand this stuff. You think I get excited about this? You think I think this stuff is important? You're damn right. I wouldn't trade what I do for anything. I've been at this a long time. And I am going to keep right going for a much longer time. With good fortune, I'm going to get what I do on Coursera. And I'm going to have the chance to talk to thousands, maybe hundreds of thousands of people about this stuff, because it's important.
Can you explain why nitrogen is more reactive, much more?
The electronegativity of nitrogen is lower than the electronegativity of oxygen. That makes the electron pair less stabilized on nitrogen, which makes the electron pair more readily available for bond formation with another species, more reactive. And we'll even talk about what underlies electronegativity when we get to chapter 22. All right, so here's our conjugate acid. Now let's go back to the paired molecule and write the formula for the conjugate base. Well, we already recognized why, with this species, the conjugate base creates a minus charge on oxygen, not on carbon. So here your choice would be, am I going to take H as H plus away from nitrogen? Or I'm going to take H as H plus away from oxygen? You already know the answer, don't you? Which H loses as H plus? This or this? The oxygen, you betcha. Because now I got that minus charge on oxygen, where the minus charge is more effectively stable, more peaceful, less reactive, and therefore, if you wish, active. And now we go on. Stuff most of you did yesterday. Well, initially, I don't all of you did this. The purpose underlying this consideration is to support your ability to get at Bronsted-Lowry acid-base chemistry successfully. Chapter 18. And you're going to see that when we proceed from chapter 18 and go to chapter 19, a whole lot of people, chapter 19 depends on this. Chapter 18 stuff. The same is said when we go to chapter 20 and 21 and 22 and blah, blah, blah. That's why we start with this. So the purpose of this is to learn how to correctly write a principal system inventory for pure substances and the relationship to acid base and water solutions of strong bronzyloric acid, weak bronzyloric acid, strong bronzyloric base, weak bronzyloric base, and that's it. There's only 5 systems. And the rules of the road for creating the inventory are all in the notes. I trust that you've all read this by now. But I won't ask for a show of hands, because I might not like to count my hands. Because if we are going to do bronzyloric acid-based chemistry and water solution, these are the only types of systems, these 5, which we can encounter. And therefore must know how to treat for them. PSIs, or if we need to know how much, QPSI, quantity. You know what inventory is. If you work at Publix and the boss man tells you to make an inventory, or maybe it's boss woman. Oh, it's boss woman, there. I'd like to see a whole lot more women get positions of power in this world. Presidents, prime ministers, you name it. There's a men that done one hell of a job messing it up. So the boss says make an inventory, you get out your scratch pad, you run around the store, and you make a list of all the stuff you got. And if the boss says quantify the inventory, you make a list of how much. And in chemistry, if we're going to how much, we how much in what unit? Moles. System, pure substance. This is a pure substance. Hey, if I give you sodium chloride, common table salt, I'm giving you sodium chloride. And I mean, I got to emphasize this stuff because a lot of students are mystified by this. Which is another thing. We who try to communicate to you this stuff, we have got to be sharp, clear, and exact as best as we can with our language. That's why I find OH minus and hydroxide line abhorrent. Stands in the way of chemistry. And the people who continue to do this on the basis of tradition, I just get furious with. Tradition be damned. We're trying to understand. HCl gas is HCl gas. Sodium chloride, ionic compound, so it's sodium chloride. Now if you wrote sodium ion chloride ion, I wouldn't be too upset with this, because NaCl is not a species. This thing is composed of these species. These are species. This is a species. An atom, a molecule, an ion. Those are the only types of species which we are concerned with in chemistry class. And now we go to the solution. The solution of an ionic compound, as we've already recognized, generic name for any ionic compound is salt. At minimum, when salts are dissolved in water, they dissociate. So you're always going to wind up with component ions of the salt that was dissolved, or other ions that were produced by reaction of the dissolved ion. I wrote that. Simple example, 100 milliliters of 1 molar sodium chloride. Notice that when I give you, in addition to concentration, solution volume, then you can always quantify the inventory. You always write 2 psi. But if all I give you is this, you cannot give me a quantitative inventory. What have I got? One drop of this solution or a swimming pool full of it? Hell of a lot of difference in the amount of sodium chloride I have versus swimming pool versus the drop. In 100 milliliters, I've got a 10 bowl of each of these ions. You can put the AQ tag on there if you wish, just for the convenience to yourself and whoever reads what you drink. But you know water is soluble. And about 5.5 moles of water liquid. You remember talking earlier on? That we did this in discussion class? About a quantitative inventory for a liter of water? Or put another way, what's the concentration of water in pure water? Remember doing that? About 55 molar. And in 1 liter of water, you've got about 55 moles of water. 1 more aluminum nitrate solution. Aha! This leads us to another consideration. That consideration being that metal ions, which have appreciable positive charge densities. What is that? Positive charge density. It's positive charge concentration, same thing. Not just charge magnitude. It's the ratio of total charge to ion size. That gives you charge density. Like mass and volume gives you mass density. I'm talking about charge density. There's 4 ions on the board. Make it 5. Each of which have appreciable positive charge density. What do these ions with appreciable positive charge densities do when they're placed in the vicinity of these guys? Or if you prefer these gals. You think this non-bonding electron density is strongly attracted to that plus charge? Coulomb? You believe that, Coulomb? You sure as hell better. You learned about Coulomb's law in 2045, didn't you? Well, how are you going to use that too? In the main, Coulomb's law tells us a species with an appreciable positive charge density will be strongly attracted to a species with an appreciable negative charge density. And species with similar charge densities from the science standpoint repel each other strongly. Now, a loaded question. Water. From an acid-base standpoint, Brown-Savone acid base. These 2 formulas? Chlorine ion and the water molecule. This is neutral, this is a negative ion. Which of these has a greater effective negative charge density? Which one? Which one? Which one? Look at the acid-base table. See which one is the stronger base. See which one attracts H plus more effectively. Which one? Water! How about that? You gotta be careful when you think about this stuff. Just because something has a charge and another something doesn't have a charge, doesn't mean that something with the charge has got a greater effective charge density. Because in water solution, we've already recognized that HCl ionized 100% extent. So how effective would this chloride ion compete for H plus in water? Not at all! Butler says, the hell with you, I think I'm home. We'll pick it up for this one next time.